So we learned about the interval between, for example, pregnancy due. For example, we talk about some kinds of interval. So when we estimate something data, instead of we are looking for exactly probability of the data equals some kinds of value, we are having some kinds of interval. Um, this interval is called the confidence interval. So later we're going to talk about how much we are confident about our probability that some value is between this range. And this data head is a point estimator and M is marginal error. And basically this data head, which is estimated from sample, and this M marginal error, those are random variables. So for example, how it's working is, let's say we are interested in find SAT score. For example, I just estimate that the people who attend the Albany has average SAT score of 1500. I just made up. So I'm just looking for probability that someone's score is plus minus 100 of it. For example, plus minus 100, this is a margin of error, margin of error. So basically I'm asking, okay, 1500 minus 100, comma 1500 plus 100, or vice 1400, comma 1600. Those are basically our confidence interval in this example. So, okay. Okay, the estimator is correct if data lies in the interval. In other words, I mean, if this interval is, for example, something, let's say somebody got SAT of some, like, let's say data. This is a true value of this. If this is inside of this range, then we says the estimation is correct. If it's outside, then it's not correct. So it's referred as the confidence level, how confident you are based on your confidence interval. So check it out, this terminologies. This interval is confidence interval. And based on this confidence interval, probability that this data to the value is between inside of this confidence interval is confidence level. So for example, the interval, I mean, this is another type of example. I mean, which of them is more likely to be correct? So of course, I mean, of course, this would be the answer, right? I mean, it would be much higher chance that the infant is born between this range instead of that. So because they have a larger margin of error. So answer is B. So because it's much wider. So consider on interval from January 1st to March 31st, it would be almost 99.9% chance, you know, it's almost always correct. But it doesn't give you anything. I mean, everyone can say that. I mean, for example, I mean, one can say, okay, I mean, you're gonna give birth sometime in the future. Everyone can say that, but it doesn't give you any information. So a narrow interval with high confidence level is the best. So for example, doctor may say, okay, you're gonna give a birth between this period with 90% chance, or this person with 95%. But given something, same interval, if you have a higher confidence, that would be best. So there exists trade-off between confidence level and margin of error. Of course, higher margin of error, it will give you a higher confidence level, but it's definitely some trade-off. So in practice, we set the confidence level for typically 90, 95%, 99, but these two are most commonly used. So the margin is determined then by the confidence level. So based on these three, so which confidence level will yield the widest interval? The answer is 99%, right? because let me show you why. Because it would have wise the interval so that the probability would be higher, right? So margin of error is much higher with higher confidence level. The higher margin of level indicates it's gonna be have a widest interval, right? So we consider estimation of mu. We know that X bar is the best point estimator of mu, right? So that was from law of large number. Consider a confidence interval like X bar plus minus M. So the M was margin of error, right? So the estimation is correct if the true parameter is inside of this range. So usually alpha denote the probability of error. So you're gonna use this alpha a lot in this course later, I mean from now on. This alpha denotes the probability of error. Later, we're gonna learn this one is equal type 1 error, but I will come back to that part. 1 minus alpha is the confidence level. For example, if alpha is a 5% level, in other words, alpha is 0.05, so 1 minus of alpha is 95%, which is probability of the true parameter is within this interval. So this is confidence level. So let's set the confidence level. Say 95%, so automatically alpha should be 0.05. If you are considering confidence level of 90%, then alpha would be 0.1, etc. So 95% confidence level should satisfy this condition. This is very important, okay? These types of problem can be potentially on the exam. So take a look at this. So we have to find such M to satisfy them. For example, the only clue we have is this is 95%. So because X bar is the only randomness, so we rearrange such that this one would become this one. So let me show you how it's working mathematically. Okay, so we are looking at, let me just write down the inside of interval thing over here. Give me a second. So this X bar minus M mu X bar plus N. So let's subtract X bar both sides. It's gonna be negative M mu negative X bar and plus N. So let's subtract mu both sides. It's gonna be negative mu minus M negative X bar negative mu plus M. Now let's multiply negative 1. So we know if we multiply negative 1, the sign would be flipped like that, right? So it's gonna be mu plus M and X bar and mu minus M. So if we switch it out, this is what we have on the slide. So this was the basic, basically how it has been done. So that is probability that X bar between this would be 95%. So remember the central limit theorem, I'll give you this one. X bar is following normal distribution with the mean mu, and this is a sigma square over n. That is a variance, right? So standardizing, how did we standardize it? So for example, we subtract. So let me show you this one from here. So I'm gonna just keep this part, the last part, which should be over here. So it's gonna be mu minus m X bar mu plus m. So first thing is to subtract mu both sides and subtract mu, and then so it's gonna be basically negative. It's gonna be negative m and X bar minus mu, and then it's gonna be n, right? And then divide by sigma over square root of n. Divide sigma by square root of n. We know this is g, right? So it's gonna be basically, we replace this with Z. So this would be the probability, okay? So standardization would give you this. So we want to find a Z such that probability of Z between negative small z and Z equal 95%. By the symmetric, the other 5% would be equal. So graphically, this is like this. Graphically speaking, so we know this is our confidence level, right? So for example, this is and this one, these are basically 95%. So these are basically 95%. In other words, this the one I'm highlighting in red here and here, the summation would be 5%. So if you divide this by 2, because they are symmetric, each one side is 2.5% each, right? Because of the symmetric, right? So in other words, if this is a small z and this is a negative z, we know here is the probability of z, negative z and large z and small z equal 95%, right? Well, this one is basically probability of this small z is less than large z, which is what, 2.5%. Graphically, this was not true. And similarly, this one was what? This one was the probability of z large z less than negative z equal 2.5% because of the symmetry. So that was the background. Okay, so we got this. So from the standard normal distribution table, we know this is 97.5, right? Why did we looking for this? So, I mean, we covered this before, but let me briefly cover. The idea is that since this is symmetric, right? So we want to find Z here. Let me highlight in blue. We want to find the Z over here, right? So such that it's gonna be actually probability of some large z less than this z equal 97.5%, right? Why 97.5? Because this area is 95% plus this 2.5, so total of 97.5. So corresponding z would be 1.96. So that's why we get 1.96. Okay. Okay. So okay, and therefore probability of z between this number is 95%. What is best to understand this visually like that? So we have this before. Where is it coming from? It's over here. I just show you how to derive that, right? So and this is equal 95%. So that means 1. So this m would be equal like that. Why this is the case? Because this one, m over sigma over square root of n equal 1.96. Where did we get the 1.96? It's over here, right? So it's basically over here, this graph, right? So basically, I think this. Yeah. Let me just. Do I need to turn it off? Okay, much better. So basically, the probability that z, I mean, the large z is between negative z and z equal 95%. The corresponding value was actually 1.96, right? 1.96. That's why this was okay. So we know this probability of basically a z. From this slide, we know this one was 1.96, right? So in other words, this one, m over sigma over square root of n equal 1.96. In other words, m is like that. So if we do the little algebra, just multiply sigma over square root of n both sides. This is how you get that. So the 95% confidence interval would be like that. So this is how you get that. So previously it was x bar plus minus m, but now you're replacing the m with this. So this is your 95% confidence interval. So however, sigma is usually unknown, so cannot be used in the estimation. So you need to use sample to estimate the s. So s would be square root of 1 over n minus 1 because this is sample and the mass is the same as before. So you are just replacing s from sigma. So that's it. So graphically, that was the visualization. So x bar plus m and the x bar minus m. So previously it was z, right? So again, this concept is a little bit different because this one was when I standardize it, right? But when you don't start, when you are not standardize it, it's gonna be usually you're finding probability that the x bar is like a plus minus x bar plus m, x bar minus m. So this one is 95%, something like that. So find the probability that the true parameter is inside of this is 95%. So, but you normalize it, standardize it, something like that, subtracting mean and divide by standard deviation. This would be your, how you get the final answers, okay? So, okay, so this was this, and then suppose that we want to 1 minus alpha confidence level. In other words, previously the 1 minus alpha is the confidence level. Alpha was what? So we learned alpha was probability of error, right? So that's why 1 minus alpha is a confidence level. So so this was this. And then remember z alpha over 2 satisfies this, right? This was, for example, if alpha is a 5% level, this would be z sub 2.5% or 0.025. So that is how you find it. I mean, this is like a notation. Because based on, we are trying to define z based on this alpha level. So because this is actually coming from something like here. So because this one probability that z less than 1.96 is this, and therefore this. So okay, this is basically 2.5, which is 5, which was alpha divided by 2, etc. So we are getting actually alpha over 2 equal this. So by symmetry, this is the answer. So just substituting. So therefore 1 minus alpha confidence interval is x bar plus minus z alpha over 2. And this was a standard deviation. Again, that was coming from here, okay? A previous slide. Okay, so there are a couple of actually confidence level that is going to be used this course. So Z sub 0.05 is usually 1.64. You might want to check it out. I mean, I already explained it chapter 5. I actually chapter 6 how to find this. So you might want to check it out again if you're confusing. So Z 0.025 is 1.96 and 2.584. Z sub 0.005. So these are mostly common used. So this one is alpha equal 10% level because alpha equal 10% divided by 2 equal 0.05. So this confidence level is, the last one is for this. And this one was 95% or alpha equal 5% because 5% divided by 2 equal this one, etc. This was 1% alpha or 99% confidence interval. So margin of error for 1 minus alpha interval is like that. So it determines the width of the interval. So as the confidence level increase, so as the confidence level increase, z alpha over 2 increase as well. I mean, that makes sense, right? Because as you want to be more confident, then of course your interval should be increased. As a result, this one should be increased because holding S and square root of, I mean, this sample size constant, only way you can increase is just increase Z, right? So interval need to be wider for higher confidence level. On the other hand, holding Z and S constant, if a sample size increase, right, the margin gets smaller. So the same confidence level can be achieved by a narrower interval. So that is actually working something like this. So no, actually, let me just, I mean, graphically, this actually, this is how it's working. So as sample size increase, right? So as the sample size increase, it used to be something like that. So this one used to be, let's say 90%, this one. But sample size increase would give you smaller variance. So this one area now became 99%, something like that. So this is just one of the example I just drew, but definitely this is something you can think about. So because as the sample size increased, this S over scalar of n, that was what? Standard error, that actually decreased, right? So smaller standard error means what? It's going to be much narrower. So it's like that. So okay, so another way of doing it is as a sigma square or S square, this numerator increase, the margin scale larger. So basically that is, so given same, or I mean, this one actually you can think in terms of like this. So let's say this interval from here to here was 90%, but as the sample size of n increase, as n increase, you don't need this interval. For example, you just need it from here to here. So the interval actually shrink. That was the point. I mean, this one and this one are same, but you can understand both ways. But another way of doing this is as a sigma square increase. That means what? If this was the original function, it becomes wider. So in other words, to achieve the same 95% interval, the interval gets wider. So that was graphical explanation of it. Okay. Okay, so length of stay in the hospital. So these are the probability. I mean, you can calculate the mean and variance, right? So I'm just skipping. So, but if you have any question, I'll go back to chapter 3 and 4. It's gonna be I explain in detail. So sample size n, x bar 1.5 and s square this. The 95% confidence interval is given by something like that. Why? Because this is 95%, so the z would be 5% alpha divided by 2. So this is your answer. And s, this was standard error. So s over square root of n, you just plug in. So this would be your answer. So approximately using calculator, this is 0.131, which is marginal error. So the error would be between this and this. So that would be your confidence interval. So within 95% confidence interval here, the probability that the true parameter is between these two numbers would be 95%. So, I mean, we know that that implies with the 5% probability, you're gonna be wrong, right? So, as I mentioned, the confidence interval will be different for different confidence interval. If 99%, then it's gonna be like that. With 90%, it's gonna be different. So you might wanna try 90% as well, whether you're gonna get the same thing. Let's say this is actually based on this information. What would be 90% interval? So you might wanna pause. I mean, this kind of question I can ask in the exam. So you might want to practice. Just go back to your slide and just whether you can get that. I'm just going to reveal the answer. So it's going to be this because 1.64, which is Z 0.05 because the alpha is 10%. So plug in number, this is your marginal error, X bar was 1.5. Here X bar was 1.5, so plus minus this one would be give you this answer. So smaller margin of error, larger error probability. So I mean that is something we went over. Consider two purposes. So estimate the demand to expand the facility and tell the patient's family about the future process. In general, cost of error is much larger in the former case. It's very expensive. So which confidence level would you use for each purpose? Before I leave you, just think about it. Since the cost of error was what? Error was alpha, right? So if this is 90%, confidence level, what is the error? Error is 10%. This one, error is 1%. This one, error is 1%. This one, error is 10%. Okay, based on that, what would be your answer? The higher confidence level has a smaller error probability, so safe when the error is costly. So you wanna choose something with small, larger confidence error. Level, so smaller confidence error. Yeah. So the only way overcome this trade-off, I mean, there are some trade-off, you know. I mean, as we discussed before, I mean, definitely having larger margin of error would give you higher confidence level, but it's less informative. So to satisfy both of them, we want to increase the sample size. Because what? Margin of error was S over square root of n. The higher square root of n holding this constant would actually decrease the standard of error. So having same alpha used to get the smaller margin of error. In other words, it's gonna be, because higher n means smaller standard of error. That means you're gonna have a smaller margin of error. In other words, interval would be smaller given same confidence level. So those were the ideas. And okay, so let's say estimate the demand for a renovation, fix the confidence interval at 99%, the margin of error would be like that. But we think it's too large, so we want to error smaller than that. I mean, I ask this kind of question in your homework. Potentially, it's going to be on your exam, so take it seriously. So only way to do is increase the sample size. So in the homework, and I ask you, okay, given this, what would be the minimum sample size to satisfy this? How you do is, currently we have this is margin of error, but we want it smaller than that. So I want to smaller than this, but this is margin of error 2.58 is coming from this 99% confidence level, right? So in other words, S is given, right? The only way I can change is square root of n. So do little more algebras. For example, multiply square root of n both sides, divide 0.11 both sides. So this is your mathematics, and finally do the math, and it should be greater than 15.71, and you scale both sides since n cannot be negative, so only taking positive number would be this, so it should be at least 247. It cannot be, it should be integer, right? So keep that in mind, and 90% confidence interval has margin of error this, but want to reduce the margin down to this. What should be your sample size? So try to do this. Just pause this video and try to do that. The margin of error would be just, you want to be smaller than this, and z sub 0.05. Choosing this is absolutely important. So this is 1.64. We had the s, and this one do like that. So finally, you'd get, it should be at least 121. Same thing. Okay. Okay, exactly same type of question, but with a different thing, like a presidential election. I mean, this one was based on the old example past elections. You can actually take a look at how the one can get the ideas, but it's just based on the binary variable. We know mu equal p, and then sigma square variance equal p times 1 minus p thing. I mean, that we learn in chapter 5. So And basically, it's gonna be exactly the same thing, but I'm gonna skip this now election part, but because it's gonna just repeat the question. So I'm basically asking you what would be the required sample size and like that, exactly the same method. But just take a look at that, okay? I think the last thing I want to discuss would be this student T distribution, because the election problem is the same thing. So I'm just skipping now, but it doesn't mean you don't study. Please take a look at. Idea would be saying, let me know if you have any question, right? So textbook has two separate chapters. So confidence interval for mu when sigma is known and this is unknown. So when sigma is known, we can calculate that using z-score, right? So when central limit or confidence level, we can calculate the confidence level like that. But if sigma is unknown, before that, central limit theorem, normal approximation fit the better provide when n is sufficiently large. That is actually when you have a large sample size and you can approximate something, any distribution with normal distribution. That was the idea. But thing is, when sigma is unknown, then you are using S instead of the sigma population parameter. So in fact, students define the t-step by this. I mean, looks exactly same as z-score, right? The previously z, but you can use z when it's normal distribution, or we know, when you know sigma, but when you don't know sigma, you need to use a t distribution. So t distribution only has one parameter, so degree of freedom, which is just n-1. So so depending on your sample size, your actually answers would be different. I mean, for example, we know 95% confidence interval and the corresponding z-score would be 1.96, right? But t-distribution, it would be different based on the sample size or degree of freedom. So in your textbook, they have some kinds of t-distribution. Let me show you. For example, let me show you that. I mean, you can Google just student to T distribution table, and it would look something like that. As you can see, these are basically the things you're looking for. For example, if you're looking for 95%, then you'd be looking at 0.0 to 5, like in z-score. And let's look at, you have only 30 sample size, n equal 30, then you look at 30 minus 1, which is 29. It's gonna be 2.045. It used to be 1.96, right? 1.96 in the z-score, or when you have sigma is known. But as you can see, it was really high when you have a smaller sample size, but it's getting smaller and smaller. But in the end, when you have an infinite number of sample size, it's going to be shooting to 1.96. Same thing as before, right? So basically t distribution and then z-score are basically the same, but when it's same if and only if it has an infinite number of sample size. So basically when you have enough sample size, more than 250, etc., I mean, it's going to be very close to 1.96 anyway. So, I mean, the idea was when you don't have actually enough sample size and sigma is unknown, you would use student t distribution. So, and then instead of a central limit theorem, we can approximate the sample distribution by t distribution. So instead of using central limit theorem saying, okay, if the sample size is large, everything can be approximated by normal, so you can just use a t distribution instead. So problem is x has to be normally distributed. So it's got to be normally distributed. For example, it can approximate binary variable. So problem 2 is, as the sample size increases, t distribution converges to standard normal distribution, as I show you just now. in my opinion, I mean, student D distribution can be replaced by standard normal as long as n is large. So it doesn't make much difference. So the name remain T distribution open remaining this one. So as you can see, as the sample size, this is degree of freedom. As this is large, you're gonna have normal distribution. It's gonna be about the same. But imagine you have a much higher sample size, it's basically practically equal. So thank you so much.